guys, so in the last example, I said that we did a one proportion t-test, right? So I want to talk a little bit more about what's going on when we're doing a one proportion, one prop or proportion. Z-test, all right? So, first of all, our test statistic is going to be Z equals, remember our test statistic is always going to be, statistic minus parameter divided by the standard deviation of the statistic. In this case, if we have a proportion, that's going to be P times 1 minus P, all divided by N. Okay, so this is our test statistic. I want to talk about different ways of interpreting this test statistic, and actually I think I'm going to move this over here real quick. Because there are actually a couple different ways of interpreting it. Let me make sure that I get this. If we have an alternative hypothesis that says that our parameter is greater than our parameter of our null hypothesis, right? Then what we're going to be looking for in terms of a normal curve is going to be that area, okay? So if that's C, all right? The other case that we're going to be looking at, if we're finding some sort of a probability, is that our alternative hypothesis is stating that our true parameter is actually less than our hypothesized value. And in that case, we're going to be looking at this shaded region, right? So these are single-tailed probabilities, right? But there is also the case that our alternative hypothesis is that our parameter is not equal to the hypothesized value. In which case, if the value is less than, or if it's greater than, we're going to have to look at both of those probabilities. So there we go. Those are our different outcomes. So let's go ahead and do a problem. This problem is not two-tailed. I really like to do a two-tailed problem. But okay. Here we go. On shows like American Idol, contestants often wonder if there's an advantage to performing last. So to investigate, researchers selected a random sample of 600 college students and showed each student the audition video of 12 different singers. For each student, the videos were shown in random order. So we would expect approximately 1/12 of the students to prefer the last singer debut. Assuming the order doesn't matter, in this study, 59 of the 600 students preferred the last singer debut. Do these data provide convincing evidence at the 5% significance level? So remember, I talked about that being an alpha level. So at the alpha level of 0.05, that there is an advantage to going less. All right. Let's go through this thing. I'm trying to, first of all, we would expect 1/12 of the students to refer the last thing in the review. That's important information. Okay, so let's go through phantoms. What is our parameter? So, we're looking at, and let's actually just go ahead and state that our parameter of interest is the true proportion. You can say true. That's what we're interested in. Okay? Alright. So what do we want to know about the true proportion of students who prefer the last Singer review? Well, we want to know, and that's what we're going to say with our hypothesis. Is it the case that it's not? I keep doing that. Is it the case that P and it's not P? That's enough. Sorry. All right, and what would our alternative hypothesis be? It should be greater than, right? This hypothesized value is what would happen if it was just strictly by chance, right? If it was only by chance, the last singer would be chosen only 1/12 of them, right? Because there's just 1 in 12 chance, right, of the last singer being chosen. It makes sense. So then, our alternative hypothesis then is that P is greater than 1. All right, the hypotheses have been stated. All right. So now we're going to go on to, I'm going to need P hat there in a moment. A. A stands for assumptions. Oh, what do we need to check? We need to check if it was, right, we need to, remember, check sin. Okay? Make sure you don't commit a sin and not check your condition. Sin S. Did it come from a simple random sample? Does it say in our question that that is the case? A. Random sample. Yay! And you want to say, actually, the data comes from a random. All right. Is each you don't really need to check for independence on this, but it's good to know, right? Yeah. Definitely each trial is independent. They don't the probabilities don't affect one another. But more importantly, right? Let's check the n and see if it's normal, right? We need to check for large counts. Also, with this SRS, is it the case that n is greater than or equal to 1/10 of n? I'm going to say that checks because what have we got? 600 students. Do we think that this is less than, sorry. So that would be 60 times 600 times 10 is less than or equal to n. Is it reasonable to think that there are more than 6,000 students? Yeah. Right. So, what are we talking about here? We are actually talking about students, though. We can't generalize about the entire population of people that watch these shows. We can only generalize about the population, these samples. So, and we're talking about college students. Yes, it's fair to say that there are more than 6,000 college students, right? They didn't say college students from one college, so perhaps they graphed them from different colleges, and then we are able to actually generalize about college students in general. All right. Oh. Okay, so now let's check for large counts. If we're going to check for large counts for a proportion, we need to know that NP is greater than or equal to 10. And we also need to know that N times 1 minus P is greater than or equal to 10. So, that's right. Sorry, I knew there was something going on. We want. Okay. Huh? Yeah. So 600 over 12, essentially, right? Greater than 10, check. How about 600? Oops, we're going to multiply. We'll go with 600 times 11 twelfths. That's going to check as well, right? So have we checked all of our assumptions? I think so, right? Yes, there we go. So now, N, name the test. We will perform a one proportion Z test. I guess I don't need to make my T's like that, but all right. T. Let's get our test statistic. All right, that's going to be Z equals. P hat. Has anybody calculated P hat for us? Pretty hot and temp.
Oh, you mean Z? Z, yeah, Z.
We need P hat first. We need. Oh my god.
P hat is 59 over 600.
Yeah, 59 over 600, which is approximately. How about this? This is what I do in this case, all right? I go ahead and get out my handy-dandy calculator, because if I put this in my calculator, it spits out everything I need right away, and I can do all my calculations at once rather than doing a bunch of calculations. If I do a one proportion Z test on my calculator, it gives me everything I need. So let's go ahead and do that. I can just do that using my regular scratch pad on my calculator, and I can hit menu, statistics, and I go to stat tests, and we do a one proportion Z test. P naught 112. Successes 89.
No,
59 over N was 600, and our alternative hypothesis is that our statistic is greater than P naught. We go ahead and hit enter, and we get our p-value. What I was really interested in right now is p hat. So approximately 0.098. We have to put this in our formula, even though, yes, our calculator just gave us the answer, right? We'll talk about how to interpret that here in a moment.
I got it.
What? Oh, because you used a table. Did you use the table?
No.
Okay, let's see what happens. All right, so this is 0.0. Darn it. .098. .098 minus 12. Well, oops. I really do want to express this as a decimal. It's just going to be nicer. So 1. Remember, guys, if you want a decimal to spit out from your calculator, you just put a decimal in your fraction, and then it says, "Oh, you want a decimal answer." So 0.083 is what I'm going to put in here. All divided by the square root of 0.083 times 1 minus 0.083, all divided by 600. Let's see. Our z value is right here, it's this one, right? 1.3292. So that's why I put it in the calculator right away, right? Because then I'm putting stuff into formulas and then writing down my calculator output. So 1.329. If you wanted to, you could look at the table and figure out where that was, but you've already got probability there. Yeah.
Yeah, but isn't this supposed to be the statistic minus the parameters? So 0.83 minus 0.098. Yeah, because the statistic minus the parameter was the standard deviation.
So our statistic is the proportion that we got from our sample. Yeah? So this number is always going to be from the sample.
From maybe the sample of the frequency and then you test it with the frequency. Now with the parameters.
Our parameter is what we're saying about the population as a whole. So the reason why our parameter is 112 is because we're assuming that if indeed there is no preference, right? If indeed it doesn't matter if you go last or not, right? Then you would expect that the population in general, like if you did it over many trials, right? So like imagine the entire population of people being chosen on a show, that the last person would be chosen 1/12 of the time. You know what I mean? So that's why it represents the population. If there indeed isn't some sort of thing in a person's mind that sways them to choose the last singer, then it would be the case that the proportion of times that a last singer gets chosen should be 1/12 in the long run for the whole population. Yeah? Okay?
Right, well, then that being said, then shouldn't the standard deviation part shouldn't it be 0.098 instead of 0.3?
I believe we use P naught. Okay. So we've calculated that. We need to obtain a p-value. Oh. Obtain a p-value. Okay. So what are we looking at? We're looking at the probability that that p is greater than 0.083, which is the same thing as the probability that z is greater than 1.329. I was right before. I need to stop not second guess myself like that. Sorry. 0.083. That's good. Thank you. I left the 0 out. Alright. Which turns out to be, well, let's draw a picture of it first, right? So we've got a z-value. If we are looking at standardized values, right? Remember that for our normal distribution, our mean is always at 0, right? Almost the right one. Which means that we're looking at a value 1.3 standard deviations above the mean. So we're calculating this shaded region. It's just really nice to draw a picture of it, just in case. And that is a 0, it's a forward-looking 0. Just in case for some reason a reader doesn't understand, you have a picture of it there. We have this value. It's on our calculator right there. So if you were to go to your table, right, and figure out what the area of that shaded region was, it turns out to be 0.09186. So let's go with 0.092. Approximately 0.092. Okay. So we obtained a p-value. M, let's make a decision. These are quite long problems, aren't they? Let's make a decision. Make a decision. Let's make a decision. What are we going to do? We have our alpha level is 0.05, right? We have a p-value that is greater than our alpha level. So our p-value equals 0.092, which is greater than 0.05. And when that happens, we fail to reject the null hypothesis. Okay? So I'll usually write H naught, but I'll write null hypothesis this time. So now it's time for S. State your answer in context. Right. So, you say there is not convincing evidence. Convincing evidence that so you want to say that the proportion Sorry, I'm struggling with the wording of this because I want to say people who choose, people who are last. That doesn't make sense. Sorry, I'm trying to word this in my mind better.
People with the rest of the last.
Yeah, that's good. Therefore, it does not that there is an advantage to going left.